All right, so today we're going to continue our discussion about why data is messy, what that means, and what we can do about it. So, imagine that we have data that doesn't have the messiness of the types we were talking about last time. So all of the data is of a known type, right? We were talking about strings and integers and things like that, so we don't have any issues like that. We also have the string values, which can be categorical or whatever. They have sort of consistent and understandable values inside them. There's no missing values that are weird, and all the numbers are in ranges that we sort of expect. So we don't have negative ages or something like that, right? So if all that stuff was true, you might be thinking, hey, we gotta be on the right track. This has got to be looking pretty good. Turns out, no, right? So we've been looking a little bit at some San Diego Police Department data, right? So when we unpack that San Diego Police Department data, you probably noticed that there were some issues. So one of the ones that pops up, the data types are not always totally right. So for example, there may be a field that says true and false, and then it also has false that's not capitalized or is all caps. So there's a little bit of work, but it's not terrible. There are also some fields that have really good consistent values. So, for example, the case type and sex have well-defined ones, but sometimes the way they're defined is not super helpful, right? So it's good to go in and join on other tables or use calculated fields to sort of clean things up to make them more human readable. Age actually had a number of problems. So one of the problems is there are some really extreme values in there that don't make sense, right? Drivers getting pulled over that are 0 years old. But also, if you plot a histogram, a plot of the frequency, the number of occurrences of each year, each age, you see these spikes at round numbers. So like there's a lot more 20-year-olds than 19 or 21 or 22. And the reason for that is that officers, in many cases, guess at somebody's age based on their appearance, right? So if they don't know the exact birthday because the person doesn't have ID or I don't know, they're just guessing. And so there's some really strange artifacts that come out of that, right? And that's a really pernicious example because it's something that you're not going to see in Outliers, you're not going to see other ways, and it's hard to figure out even what to do with that because you may want to like eliminate all those, but there's actual people who are really 20 years old, so you don't know which ones are guessed. It's just kind of gross, right? There's also missing values that we don't understand in there. So sometimes age will be just me missing or whatever. We're going to talk about some approaches for why that might be missing. Also what to do when there's missing values that we do understand. So we'll get into that some. One thing I think that it's worth spending some time on is thinking about how data is collected and how that can affect things. So in this case, this is Cook County, which is Chicago. They had a dog licensing website, right? So you go and put your thing in, and there are hundreds of different spellings of the dog breed Chihuahua, right? Which I would not have guessed that right on my first. I probably would have gotten it by 250, but like it's pretty weird, right? Obviously, this is a debacle from a data science perspective. If you want to group by, you sort of want them all together. So one way you can fix this is you can limit choices, right? But you also need to be really careful in the selection process what those limited choices mean. So, for example, if you look back on historical records in the 1860s, for the United States Census, there were only 3 options, right? It was white, free black, and slave black. There weren't other choices available, and obviously there were Native Americans and Hispanic folks and all these other things. So sometimes when we really severely restrict the options, it's bad data, but also it has social problems, social harm. So figuring out your taxonomy, your data categories is super important. In fact, mixed race people, allowing people to select more than one race, is a very new addition to the census. I think that was the Obama administration. So this has been a constant evolution. Obviously, it's not just race data, right? If you have a dog breed that is not listed, you could be pretty frustrated also. Okay, so now we're going to say all that's good. There's another type of data issue that shows up a lot, which I'm going to broadly call non-stationary data, which really means data that evolves, changes over time. So one thing you can think of here is that in general, over a year, the low temperature in San Diego is like 57 degrees, which is like nice hoodie weather, right? But if it's July, it's not the average, right? It's non-stationary. It changes over time. So you have this thing where, like, knowing that extra piece of information, you don't need a sweater in July, right? So when you're collecting data or processing data, it's really good to be aware of that, and it shows up in unexpected ways sometimes. So one of them is this example where Sheldon graduated from the computer science department like 10 years ago. Got a entry-level job, $60K a year, and over the last while has worked up to $68,000, right? And so the question is, is that good, right? And it turns out that we have inflation in this country. Right now, 2020, it's incredibly low, right? But over time, inflation compounds, and it turns out 68,000 is less than the 60,000 in 2010, just accounting for inflation. So Sheldon is actually earning less money now, even though the number is bigger. So it's really important to think about these baselines and how things evolve over time, especially if you have time-limited samples, right? Assumptions from the past may not be true in the future, and your models may break. So there's this thing that a lot of people were taught at one point in a science class about how you can just get rid of outliers or incorrect values. And I want to encourage you to be really thoughtful about this. There's no strict rule that says if something is 3 standard deviations outside the mean, you can toss it or anything like that. In my mind, throwing away data that you don't understand why or you don't understand the effect is bad, right? You really need to have a good idea of what's going on. So often the data is bad because of part of the data ingestion and recording process, right? So we talked about some special values before, like if you just constantly see the year 1899, that may actually be a missing value that is a default. If it's consistently wrong like that, and you know what it is, you can fix it, right? So no problem there. If you know what it is, in that case, it's a missing value. You just delete all those and move on. There's other times, like with Chihuahua, that you can go through and just fix the spelling, and you can be relatively confident with what you're doing. There's other cases that are less clear. So it may not be totally nonsense, but it might be some weirdness. So we had those spikes in the ages of people who interacted with the police, and we could try to do some work around there. So we could make 5-year bins, and those bins would sort of smooth out the effects of guessing at age a little bit. We could also try to like spread, I don't know, there's a bunch of different techniques you could use. It's not clear what's best there. And more broadly, when you have weirdness in the data collection space, you kind of need to think about why that weirdness is happening and what the actual real world answer would be, and if you can get at that knowledge, or if you can gloss over it in a defensible way that still gets you at the truth, right? One thing to remember is the data is not reality, and what you're trying to do is understand something real in the world. And so whatever you choose to do should try to get you closer to that real thing. Another category is these outliers, right? So if you see somebody's age is 200 or it's 2,000 degrees outside or something like that, maybe you should throw it away. In fact, what you should probably do is dig in and figure out how it got there. So maybe the data is real. Maybe it's part of the collection process. I often find when I dig in on really weird examples like that, it shows me that something's broken in an unexpected way, and it's affecting more than just that one point, right? There's like other stuff in there, and I should figure it out. So, cool. One thing we've mentioned a couple of times is missing data. So here is it's actually a little bit of a different format than the one we've been working with, but this is some police traffic stop data. You'll notice a couple of things. One is the service area column. They actually are treating as a string, and they write unknown in there. So that's really a missing value, but it's being categorized as its own, or labeled as its own category, right? Similarly, with some of the other ones, it's not immediately clear if subject race, if all of the letters correspond to races, or if one of them means unknown or something like that. So you'd have to look that up. But over on the far side, you see some things where it actually says where there's just missing values. So one of the columns is just missing San Diego resident, so it's not a yes or a no. And it's not clear sort of why all these things are happening. You may even see some real weird placeholders, like stop time could be -1 or 0, and that's a missing value. So once you've identified these missing values, what can you do? One thing that's helpful is to think about a taxonomy of missing values. So missing by design means that a field is missing on purpose, and because that doesn't make sense in that case. So an example might be if you have a zip code field. If somebody says they are not from the United States, where they don't have zip codes, that zip code field should be blank, right? It's actually correct to not have a value there, and you don't need to do anything about that. Completely at random is an interesting case too. It's sort of the opposite, but it means that it's just intermittently not there for no apparent reason. If it's totally random, and you're talking about randomness in Data Science 10, randomness has a very specific meaning here that isn't just haphazard. It's really meaning that it has no correlation, no relationship, no association with the other variables you're looking at. If it really is a random assortment, that's a different category, right? And so an example there would be if you only selected a subset of people for a survey. With the census, for example, there's the long form and a short form, and only some people get the long form, and they're chosen at random. Missing at random is not missing completely at random. It means it depends on some other fields. So missing at random, for example, might mean that in this example that's given, somebody who is waiting tables might not report their income in the same way that someone who gets isn't tip-based might, right? So you tend to see systematic missing values in the data, but it doesn't depend on the number itself. And the final one is not missing at random, right? So not missing at random means that the number itself or the category itself is directly causing some of the missingness. So, for example, people with high income might be less likely to report their income. So there's actually this like dependence between the income and the missingness, right? A direct relationship there. So thinking about this a little bit more with all these categories, these aren't real strict categories or anything. They're just helpful ways to think about it. And really the question is, what's causing it? Is it a natural process? Is it part of the data collection? Is it people saying no? Is it signals dropping? What's going on? And in practice, it's just hard to know these things. So there's a lot of judgment and domain expertise that are required to really make these decisions. I would encourage you when you're working on data throughout this class, but especially the police data, to think about why these things might be missing, to think about what a traffic stop or an arrest would actually look like, and the forms, and imagine what the officer's doing. So, they may be typing things into a computer, they may be writing things down on paper and having it scanned or typed in later. You sort of need to think through why that could be, and then maybe in some cases people don't report things, or if it's a hit and run, for example, they may not know anything about the person. So it's good to try to tease those apart as an example. So what can you do about all this, right? If it's missing by design, it could be you don't need them at all. It could be that you can get rid of that data, right? In the zip code example I gave, maybe if you're only looking at zip codes, it's fine that you don't have the international people because you're only interested in the US. So you may be able to recode things, you may be able to drop them, you may be able to just know what the answer is. When they're completely at random, you can actually just get rid of things. So you'll learn a little bit more about this in Data Science 10 if you haven't gotten there already, but you can think of this sort of as a randomized controlled experiment, and it shouldn't affect your results if you just throw them out, as long as there are not too many. But that's only when they're completely at random. If they're just kind of randomly missing, so this is the ones where it correlates with other columns, dropping will cause problems, right? It will cause things to be skewed. And the way you can see that is if you drop the ones where income is missing, it will affect the other columns too, right? So it would affect occupation in the example we were working with. So maybe a better thing to do is to replace it with an average value, or to train a model to replace it with some sort of prediction, right? Use some machine learning there. When something's not missing at random, means that the value is missing because of what the value is. There's really not a lot you can do, right? It's extremely hard to get accurate measurements that way. There's a lot of ways to think of it, but in a big lecture class, right? If you ask everybody, hey, did you cheat on the test? Nobody ever raises their hand, but that doesn't mean that nobody has ever cheated on a test, right? And so trying to make a prediction there, you just know your data is bad, right? Missing data is a really tough topic. There are whole classes in it. I just want you to be aware that it's a messy and complicated thing. It's going to come up, and it's going to be difficult. A lot of judgment calls in there. The main thing I would encourage you to do, again and again, I keep saying this, is to go back and think about the effects this would have. Think about the causes that are making it go missing. All right. So this number shows up from time to time, and it showed up in the news this week. So I'm recording this on October 5th, and I'm recording it because this number was made worldwide headlines today. For those who are not familiar, it's 2 to the 16th power, and it's actually tied into some really frightening news about how the coronavirus pandemic has been evolving in England. So what happened is there were a number of contractors that are feeding in COVID case data to a government agency that is responsible for monitoring it. They were handing that data over as CSVs, which, again, you've seen in Data Science 10. CSVs don't have any sort of limit to them. They're just text files, so you can keep making them bigger. At some point, they become unwieldy, but there's not a built-in limit or anything. The ingest process, the data pipeline that was built by the government, used a conversion and translated those CSV files to XLS files, which is the Microsoft Excel format. It's actually the original Excel format. It's from 1987, and it has been obsoleted by XLSX, which came out probably 20 years ago. So this is an older format, but it's not unusual to have old data formats around just because that's what people are familiar with, and code tends to last for a long time. All right, what does this have to do with that number I threw out? Well, it turns out that the maximum number of rows in Excel in the XLS format is 2 to the 16th, right? So it's the 65,536. So these different contractors were making files, CSV files. They would report them in, and then the government program picked all those files up and put them in Excel files and summed them up and totaled them. But what it was doing was silently truncating. So it would only load the first 65,000 rows and just drop all the rest. So now we have missing data that we don't even know is missing, right? This caused a huge underreport in both testing and in cases, and that causes serious issues like the decisions about reopening and schools and all this thing to be made with bad data. So this is a data engineering disaster that caused real significant harm in the world. It probably killed people. The thing I want to say is missing data that you don't even know is missing is extremely common. We had at work a new release of an Android app that stopped reporting search data, and it took a while to notice just because we didn't have automated monitoring on there. And it's such a small part of the traffic that it didn't show up for a while. Extremely common. Luckily, that's much lower risk than a pandemic. But just be aware that I think that's probably the scariest type of missing data is when things are just partially missing and you don't even realize it. So, all said, so data's messy, right? We've talked for 2 lectures about this. It's super messy. Why don't we just clean it up? So clean it up can mean a couple of things. One is we can improve our data collection or ingestion process or our data pipeline to sort of before it gets to the data scientist. That's usually a good idea, but it's always going to be kind of bad. It just gets better, right? So why not just train models, fill in the values, do all that kind of stuff? The key to that is that you have to. You will do that. But when you do that, you make choices, and those choices affect the results, and that causes a number of problems. So one thing it might do is it might introduce bias into the results. So it's easy to make bad assumptions about the real world if you just don't understand what's going on in the real world. There's a collection I really like that was optional reading that's about falsehoods programmers believe. And there's a lot of places where people throw out results because they think they're not valid, right? So you think that all email addresses have to have exactly one @ sign, and if they don't, they're invalid. Well, that's just not true, right? Or you might think that everyone has to have a first and last name, or that names need to be more than 1 character long, or all these different things. And the world is much bigger and weirder than you think. And so when you go and clean it, you may be introducing serious bias into this. It can cause real harm. The other thing that's related is it may just drive you away from the truth. So if you think something's missing completely at random and it's in fact not, you can cause bias that will just lead you to the wrong answer. And since I think of data science as really science in the service of decision making, when you cause someone to make a bad decision based on the data processing you've done, fundamentally, I feel like that means you lied to them and that they were misled based on your advice and that you are partially responsible for the harm that comes out from that, right? The people that designed that data pipeline and failed to notice data was missing messed up, and their malpractice killed people. And I just hope that when you look at this data, when you're making advice, you're very careful to do the right thing, but also to think carefully about how sure you are and how your data actually reflects the real world. Cool. That's it for missing data, and I will see you again soon.